Today we're going to be taking a look at quadratic functions and models. So first of all, let's introduce what is a quadratic function. Some of this is going to be review. I know I keep saying that, but some of this will be a review for you. So what is a quadratic function? A quadratic function is a polynomial of degree 2, second degree polynomial function. That's what a quadratic function is. I have a little intro here, and this is good notation to get used to seeing, all right? A sub n, x to the n power, and then a sub n minus 1. So whatever subscript that is, this would be one subscript lower. The degree here is n, the degree here, or the exponent here is n, the exponent here would be n minus 1, so it goes down 1. And it keeps going down 1 until it gets down to 1, and then no exponent. This would be like x to the 0 power. So that is a polynomial function of degree n. And if the degree is 2, we have a quadratic function. Okay, so every quadratic function can be written in this form, ax squared plus bx plus c. Here's some information about quadratic functions. The graph of a quadratic function is always a parabola. All parabolas are symmetric with respect to a line called the axis of symmetry, or simply called the axis of the parabola. When the lead coefficient, when this a, is positive, then the graph is a parabola that opens upward. The vertex is the lowest point then on that parabola. So if your parabola is opening upward, the vertex will be the lowest point on that parabola. It's the relative minimum of the function. It's also the absolute minimum of that function. When the lead coefficient is negative, then your parabola will be opening downward. The vertex now is the highest point on the parabola. It's a relative max. It's also an absolute max. To graph a parabola, we need to first write the quadratic function in what's called standard form. The standard form of a quadratic function is like this. Okay, a times x minus h squared plus h, where the vertex there will be hk. hk will be the vertex. Okay? If a is positive, the parabola opens upward. If a is negative, the parabola opens downward. A determines the vertical dilation. Okay, let's do some examples. Let us sketch the graph of this parabola. So first we're going to get the equation in standard form. I'm going to begin by just writing h again. Now we want to get this as something, a binomial being squared. So I need to complete the square on this. So to complete this square, I might just write down the first two things. Don't write down the plus 8. I'm about to do that in a second. What do we add to complete the square? We did this the other day. Half of this number squared. Half of negative 8 is negative 4. Squared is positive 16. But we have that 8 over here. We need to keep that 8 value, so I need to subtract 8 to keep this plus 8. 16 minus 8 is 8. So I haven't changed the function. By splitting that 8 up into 16 minus 8, I have not changed anything about this function. And now we factor right here. So factor that. It should factor into a perfect square, which is why we added the 16 to that. And it does. It's x minus 4 quantity squared minus the 8 that was from that piece. So this is standard form. The vertex is 4, negative 8. Positive 4, negative 8 is the vertex. The A here, the A is positive, so this parabola will open upward. And since A is just 1, there's no dilation, no vertical dilation. So we can go graph this. So I start with my vertex, 4, -8, 4, -8. And I'm opening upward, no dilation. So over 1, up 1 on both sides of the vertex. Over 2, up 4, because it's a square. It's a parabola, so it's a quadratic function. It's squaring. So over 2, up 4. 1, 2, 3, 4 on both sides. Over 3, up 9, because 3 squared is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 on both sides. Over 4, up 16. 4 squared is 16. So let's see, I go up 8, and then I need to go up another 8 to get to 16 on both sides. And that is plenty. We can go ahead and draw the curve through here. On both sides. And it gives us a nice, really nice parabola there. Okay, let's do another one. Part of what we're doing today is just really practicing getting some good algebra back. I have several where we complete the square just so you can relearn that. Okay, sketch the graph. So I'm going to begin with what I'm given. Okay, now this time, this one is different from this one. This was easier because there's just a positive 1 in front of the x squared. Here we have a negative 1. We have to begin by factoring that out. I'm going to factor it out of the x squared. I'm going to factor it out of the negative 10x. But I am not going to factor it out of the negative 16. That is going to hang out here by itself. Okay? All right. Inside this parentheses that I just made, I need to complete the square. Half of 10 is 5. 5 squared is 25, so I'm adding 25 there. So I'll be able to factor this into a perfect square. Now, as soon as I put plus 25, I have completely changed the value of my function. I can't do that, so I need to do something back here to keep it equal. Well, I really subtracted 25 here. I actually subtracted 25. I can't just come in and subtract 25. I need to come in here and add 25 to the back. Now it's all equal. Now it's the same as this f. Alrighty. Have that negative outside. Let's factor into our perfect square. This will be x plus 5. It's always just half of that 10, half of that b value. And then back in the back now, I have plus 9. So this is the vertex of that parabola is negative 5, positive 9. And this parabola is opening downward. And again, no dilation. Because it's just a 1, negative 1, but it's just a 1. All right, so let's go graph this. Negative 5, 9. Negative 5, 9 is right here. And we're going downward in just a 1 dilation. So over 1, down 1 squared on both sides. Over 2, down 2 squared on both sides. Whoops. Over 3, down 9. On both sides. Did I do that right? Goodness. I have a feeling I'm bleeding through. Okay. On both sides like that. Okay. Over 4, down 16. So there's 9. So I need to go another 7 on both sides. And that's good enough. And go ahead and draw our parabola. So, okay, I've got a couple more here. Okay, what happens if you have a 2 in front of that x squared? Well, I'm going to rewrite the whole thing first. If you have a 2 in front of that x squared, I'm going to factor out the 2, but only from the first 2 terms, only my x terms. So x squared plus 4x, when you factor out that 2. You can double check. 2 times 4 is 8. And I still have that plus 7 in the back. Okay, to complete the square, I'm going to add half of 4 squared. Well, half of 4 is 2. 2 squared is 4. So I need to add 4 inside there. But I'm really adding 8. I'm really adding 8. So I need to subtract 8 back here to keep it all the same. So my standard form will be 2 times x plus 2 squared minus 1. The vertex is -2, -1. This parabola is opening upward, and it does have a dilation of factor 2. Okay, so we'll go to our vertex, -2, -1. Okay, and we're going upwards, dilation of 2. Usually I go over 1 up 1, but now I have a dilation of 2. So I'm not going to go over 1 up 1, I need to multiply that by 2. So over 1 up 2. That's what that dilation of 2 is going to do. Over 2, usually I would go up 4, but now I'm going to go up 8. So I'm going to go up 8 on both sides, and that will be my skinny, vertically stretched parabola. Okay, what about this one? Okay, -x squared minus 12x minus 36. So I begin by factoring out a negative just from my first 2 pieces, my x terms. Leave your -36 alone. Okay, inside the parentheses, we're going to add half of 12 squared. Well, half of 12 is 6. 6 squared is 36, so I'm adding 36 inside. But really, I'm subtracting 36, so I need to add 36. So my standard form is -x plus 6 squared. Plus 0. That zeroed out. That makes my vertex -6, 0. It's right on the x-axis. This is opening downward. No dilation. So -6, 0. Opening downward, no dilation. 1, 2, 3, 4. 5, 6, 7, 8, 9. We're going to get nice and quick doing these parabolas. These are not hard to do. Okay. What if there's a 1/2 out there? Alrighty. So I'm going to rewrite. You don't necessarily have to rewrite. I just like to. Okay, factor out a -1/2 just from your x's. So you have that x squared. Now, what do you get when you factor out a -1/2 from a positive 4x? Well, it's going to be negative, because a negative times a negative is a positive. What do you multiply 1/2 by to get 4? It's going to be an 8, right? 1/2 times 8 is 4x. Leave the space. Put your -10. Okay, what do we add here? We add half of -8 squared. Half of -8 is -4. -4 squared is +16. But really, what did we do there? Really, we subtracted 8. So I need to come and add 8. So my standard form will be -1/2 x minus 4 squared minus 2. My vertex is positive 4, negative 2. We're opening downward, and we have a dilation, a vertical dilation of negative 1/2, of just 1/2. I took care of the negative when I said downward. Vertical dilation of 1/2. So go to your vertex, 4, negative 2, and we're going downward, making sure I did that right. Yes. We're going downward at 1/2. So instead of going down 1 or over 1 down 1, I'm only going to go down 1/2 because half of 1 is 1/2 on both sides. Over 2, not down 4, down only 2. Half of 4 is 2. Over 3, I would go down 9. I go half of 9, which is 4 1/2. 1, 2, 3, 4 1/2. Over 4, I would go down 16. Now I'm only going to go down 8. So this parabola is going to be a little bit wider than our no dilation parabolas. Okay, that's how to graph getting in standard form. Okay, let's go backwards. What if we're given the graph? How do we get the equations? Okay, let's look at F. F has vertex. F has vertex negative 7, 8. And it's opening downward. Is there a dilation? I see over 1 down 1. I see over 2 down 4. There's no dilation there. So f of x will be downward, so negative x plus 7 squared plus 8. Okay. What about G? What's the vertex of G? The vertex of G is 3, negative 7. It's opening upward. Does it have a dilation? I go over 1 and I am not going up 1. It's somewhere between that. It looks like 1/2. Let's confirm that it's 1/2. If we go over 2, how far up do we go? Up 2. Yes. So we're going up half of what we should. So the dilation factor is 1/2. So G of x will be positive 1/2 x minus 3 squared minus 7. Not bad. Okay, what if they don't give us the graph? What if they just give us some information? Like, f is a parabola with vertex 512 that passes through this point. Well, they give me a lot of information here. They give me the vertex, which is really key. Yeah. What I don't know is this a that's out in front of my parentheses. But I do know inside these parentheses will be x minus 5 squared and then plus 12. I know that much. All I have to do is find a, and they gave me this point. So I can plug in 7 for x and 15 for y, and I can find out what a is here. Y is f of x, right? So I'm plugging in 15 for y and 7 for x. And that will allow me to find the value of a. Subtract 12 from each side. 2 squared is 4. A must be 3/4. So f of x must be 3/4 x minus 5 squared plus 12. I think I have another one for us here. Oh, no, I don't have another one for us here. Okay. You get some practice on your worksheet, though, so that's all right. Okay, how can we use this? Find two positive numbers whose sum is 100. Their sum is 100, and their product, I want their product to be a maximum. And we have to justify algebraically, which means we have to do this algebraically, not just go and test numbers or whatever, okay? We're going to justify algebraically. That's what I say when I want you to do it the way we're doing it, using the material that we're using, not just guess and check. Guess and check is not justifying algebraically. Okay, let's let x and y be our two numbers. Okay. Now we also have a product involved, so while I'm saying let, I'm also going to say let P be the product of x and y. Okay, so I get those things going. All right, their x and y's sum is 100, so x plus y must be 100. P is the product, so P must be x times y, right? Well, I would like to get P to be just a single variable, so I'm going to come over here, and I think I'm going to solve this for y, so that I get x's in my product function. So P will be x times 100 minus x, because y is 100 minus x. So P is 100x minus x squared, or I could rewrite that as negative x squared plus 100x. That is a parabola, and it's a downward parabola. That is a downward parabola that has a max at the vertex. So all I need to do is find that x coordinate of the vertex, and I will be all set. So P is equal to, okay, there's my function. I need to get it in standard form because I need to find the vertex. So I'm going to factor out a -1. Okay. Factor out a -1, complete the square. Half of negative 100 is negative 50 squared. Negative 50 squared is a positive 25 with 2 zeros. 50 squared, 5 squared, and 10 squared. So I subtracted 2,500, so I need to come back here and add 2,500 to keep it the same. So now P is equal to negative x minus 50 squared plus 2,500. The vertex of the parabola is 50, 2,500. So the x coordinate there, max, I'm going to say max when x equals 50. Is this the y coordinate? Is this y? No, it's definitely not y. Definitely not y. It is the maximum. That 2,500 is the maximum product. It's the product, okay? So max when x is 50 and y is 100 minus 50, which is also 50. Okay? Alrighty, let's do another one. Another application of these quadratic functions. The profit P in hundreds of dollars that a company makes depends on the amount X in hundreds of dollars that the company spends on advertising, according to this model. They very kindly give us this model, which happens to be a quadratic function. What expenditure for advertising will yield a maximum profit? Again, we're going to justify our answer. This parabola, I see that negative x squared. This parabola is a downward facing. Okay, this function is a downward facing parabola whose max is the vertex again. Okay, so if I want to know what expenditure, I want to find x. We're finding x that will make. We're trying to find out how much do we need to spend on advertising to make a maximum profit. Okay, so we have our p function. I'm going to rearrange it because I like to put my x squared first, and I would prefer to deal with fractions than decimals, so I'm going to change 0.5 to a half. So negative 1/2 x squared plus 20x plus 230. There's p. So we're looking for the vertex. I'm going to begin by factoring out a negative 1/2. We'll have x squared. Okay, I need positive 20. What do I multiply negative 1/2 by to get 20? Well, it needs to be negative to make my sign positive in there, right? And I need to multiply by 40. Half of 40 is 20. So I need negative 40 in there. Yeah? I'm going to stick my 230 back here. Okay, what do we add inside? Half of negative 40 is negative 20, and negative 20 squared is 400. But what did I really do here? I really subtracted 200. So I need to come back here and add 200. Okay, so my standard form will be x minus 20 squared plus 430. The maximum profit is when x equals 20. What did that mean again? Because x was in hundreds of dollars, so spend 20 times $100 in advertising to maximize the profit. What is the maximum profit? What is the maximum profit? The maximum profit is this 430 because it was also in hundreds of dollars. The maximum profit will be 430 times 100, $43,000. Okay? All right, one more thing to look at before we finish these notes. Let's consider some points on this graph, okay? When the vertex is at 1, -6, 1, -6, okay? The point 2, so 1, -6 is there, 2, -4 is there, 3, 2 is there, 0, -4 is there, -1, 2 is there, and if we kept on going, I could show you that these are -2, 12, and 5, 26. Okay? First of all, notice that the x values in the table are equidistant from each other. That's key for what I'm about to do. They each differ by 1 this time, okay? But we can only do what I'm about to do if the x values are equidistant from each other, and they are, okay? Now, we're going to examine the first differences between the y values, the first differences. So the difference between 12 and 2, what do you do to 12 to get to 2? Well, you subtract 10. What do you do to 2 to get to -4? You subtract 6. What do you do to -4 to get to -6? You subtract 2. -6 to -4, you add 2. -4 to 2, you add 6. 2 to 12, you add 10. 12 to 26, we add 14. Yeah? These are called the first differences. the first differences in the y values. All right, they happen to be here since the average rate of the x difference was just 1. They happen to be the average rate of change as well. If these were the same, number each time, we would not be dealing with a quadratic. We would be dealing with a line. We would just have the slope of that line. So if these are the same, the function is linear. Okay. Now we're going to examine the second differences. So what do you do to negative 10 to get to negative 6? You add 4. What do you do to negative 6 to get to negative 2? You add 4. Negative 2 to 2, you add 4. 2 to 6, you add 4. 6 to 10, you add 4. And you add 4 again. There's your constant. These are the same. If the second difference is the same, if that is true, then your function is quadratic. Now we knew it was quadratic because I made it quadratic. So I knew this was going to work because I had a quadratic here. But even if you weren't given any other information, even if you were given just a table of values, you could determine the degree of your function if it's polynomial. If it's polynomial, you can determine that degree. If the third difference was the same, if the second difference was not the same, but the third difference was, your function would be cubic. If the fourth differences are the same, your function is quartic, etc. So this is how you would determine the degree of a polynomial given only some values, as long as your x values in the table are equidistant from each other. And that is it for our notes on quadratic functions and models.